here at MIT and across the world for in many ways, and they will tell you today a little bit about the work that they work on. So we even brought some props so you guys can look forward to the actual examples and models of the satellite program. As usual, please use your notebooks to take notes and listen really intently to it, and we'll get it kicked off. Thanks, guys.
Thank you. So I brought a book too, so you should interrupt me with questions, and I'll write down the ones that I don't know the answer to. So I'm Ewan Douglas. I'm a STARlab with Professor Cobuild, and we're going to talk about CubeSats. You've heard a lot about CubeSats, I think, generally, but this is an example of two being deployed from the space station, and we'll talk more about what the different sizes mean and what you can do with them. So STARlab, the lab Professor Cobuild leads, has about 30 graduate students, a bunch of PhD students, and STAR stands for space, telecommunications, astronomy, and radiation. So it's pretty broad. We work on looking for planets around other stars that might be Earth-like. We look at how do you communicate with space with lasers, and work on how radiation impacts your spacecraft. How does it damage things? So I'm a postdoc. You might not know what a postdoc is. So a postdoc is someone who is after their doctorate. So I got a PhD a few years ago, and now I'm working as a scientist here for a few years, sort of learning more as an apprenticeship in the field of science, space instrumentation. Before that, I was at Boston University studying astronomy, where we built rockets. This is an example of one that came back to the ground. We put telescopes on rockets, and they go up to, that one went to 135 miles above the Earth, took a few observations, a few minutes later came crashing down into the desert, and then we got it back, put it back together. Before that, I worked on a big physics experiment called LIGO that tried to measure gravitational waves. You might have heard of them in the news. They just got the Nobel Prize. But I wasn't there when they made the discovery of black holes that got the Nobel Prize, but I did do a little bit of work many years ago. I studied physics at Tufts, just up the street. But I did study abroad in Africa, in Ghana, and took some physics classes there. And so now here at MIT, I'm working on CubeSats, and we're going to talk about CubeSats a lot, but these are some of the mock-ups. And we're working on ones primarily to tie back to that science question of are there Earth-like planets around other stars, and what technologies do we need to detect those. So that's been my main focus. But our lab has built a lot of CubeSats. So Micromass, the one that you saw on the first slide, was a microwave atmospheric measurement satellite. Murata, which just launched in November, is another radio instrument to measure the Earth's atmosphere. Micromass is more radio instruments to measure the Earth's atmosphere. NODE is a laser communication experiment that shines a laser down from a spacecraft and uses it to transmit information instead of a radio. DEMI is the project I mostly work on, which tests mirrors that can change their shape in space. So if you launch it and your telescope's out of focus, you can just correct the shape and focus it. And then we have more coming, more radio experiments and more laser communications experiments. So to back up a little, yeah?
The experiment where you were using lasers to get the information, how does that work?
So you can, if you flicker the laser on and off, basically, you can encode information. And if you have a narrow laser beam, you can use the same amount of energy to get more data, more information down to the ground than a radio that's shining in all directions. So you can have, with the same size battery, you can get more information down per second by focusing down on the ground.
So you could say, like, if you send a beam of light and you see a flicker, that's a 1. And if you don't, it's a 0. And just do a stream of that, of 1s and 0s. And then you could divide a chunk of time up into like 26 slots like the alphabet. And you can say, well, if I get light in slot 1, it's an A, and if I got light in slot 5, it's an E. That kind of thing.
Oh, that's cool.
Yeah.
So I'm going to back up a long ways. And how did you get to putting stuff in space? So this is not the very beginning of rockets. That you got to keep going back to fireworks and gunpowder. But Goddard built this first liquid fuel rocket in the 1920s out of Worcester. And an interesting challenge when you look at this, does anybody know which part is the rocket?
Oh, the little top bit.
So where do you think the fuel is? Yeah, so the fuel's down here, and then this is the rocket. So it went up pulling its fuel behind it. And then this tripod is just, this is the tripod that holds it up. So this structure here is the fuel, and then the exhaust came down on it. It didn't go very far. I think it went like 40 feet up and landed in someone's cabbage patch. They always end the story about it. But that's less than 100 years ago. It was this little toy rocket that landed in a cabbage patch and didn't go very high. So then we had to get, space is still much higher. So then the next big step in rockets where we actually started hitting space was liquid-fueled rockets that were originally built by Germany in World War II, and they were used to attack London. And then they were captured and taken to the US, New Mexico, and they were launched straight up. And these V2 rockets could get to 60 miles, could get to the edge of space. And they took this first picture from space at like 61 miles up. I think this was in 1947. Just putting a film camera on one of those rockets and pointing it out. I have a little video, we'll see if it plays. This is a newsreel.
Part of a flying laboratory is recovered by Clyde Holiday of Johns Hopkins, who prepared it for its trip to the...
Try and get it over there.
Flying laboratory is recovered by Clyde Holiday of Johns Hopkins, who prepared it for its trip to the upper
So
stratosphere.
this was the camera that they put on the top of those rockets. So they started with something really low tech. They just took the camera and put it on a rocket.
Of a captured German V2 rocket.
And they put it on a timer, so they would take a picture every few seconds.
Air Force pictures show the rocket in flight, and the flying camera automatically takes over. The huge projectile drops the Earth behind at the tremendous speed of 4,000 feet per second. The rotation of the rocket causes the planet to spin before the lens, and the camera photographs the Earth 65 miles straight down. The horizon, 720 miles away, and the curvature of the Earth are astonishingly apparent in this still picture from the film. An observer in the rocket could have seen San Diego, Salt Lake City, Kansas City, and San Antonio. Approximately 1,600,000 square miles of the Earth's surface was revealed. The rocket reached the 65-mile height in 3 minutes.
How many of you guys have seen a real rocket launch? Every so often there's one that will go up the coast from Wallops, and you can actually go outside here and see one of the stages separating if you know where to look. So you can sometimes see rockets from here that are launched way in Florida or Virginia.
So the one thing to remember there is that they were using very simple off-the-shelf technology. They took a camera and they put it on a rocket. They didn't build a whole spacecraft and build a custom camera. There was some modification of that off-the-shelf camera, but they started with something that they already had and then adapted it to a spacecraft. The first orbiting spacecraft was the Soviet Union's Sputnik, and this was like a 58 centimeter, I think it weighed about 80 kilograms, like a 170 pound sphere. And it was actually, they pressurized it to more than the Earth's atmosphere. So they didn't have to worry about whether the electronics would work in space. What the environment of space was, they were like, well, it's a vacuum, it's all this radiation, so we're going to make a big heavy sphere, fill it up with nitrogen gas and batteries, and then launch it up and have these big antenna so you could hear the classic Sputnik tone. And then, but it's still not very big and not very complicated. And then the US's first payload was also pretty small, so it was this was the whole Explorer orbiter, and it had a Geiger counter, some temperature sensors, some thermometers basically. It had different ways. They had little microphones basically to try and measure how many micrometeorites would hit the device, because they didn't know what the space environment would be like in terms of how many asteroids or little bits of dust were there, would they run into you, and would it be unsafe for an astronaut to be up there. So they put little microphones and measured the impact. And then they had batteries and a radio to measure that. And this was all done, like they calculated all of the trajectories by hand. You might have seen the movie Hidden Figures. There was another group, so they were at NASA Langley, and these women were the human computers at JPL, and they did Explorer's trajectory. And then things got more complicated. So we went from taking a simple off-the-shelf thing, like a camera or a microphone, and we went up and built the space shuttle and many more full spacecraft, which obviously you can do a lot more. You know, this is the cabin. You can store a whole space telescope here. So the space shuttle gives you a lot of utility. It's like a big pickup truck to go to space, but it's also very expensive. And every experiment you put on it has to be safe to interact with humans. You don't want to injure the astronauts who are deploying it, so it costs a lot to make sure things are safe. And that's still true now at the space station, where you saw those first CubeSats in the first picture. But there's lots of other big uses of space now. We have communication satellites, which Professor Kahoy used to work on. He knows a lot more. Are any of these ones you built, or?
They look very similar. So not Intelsat 14, but TerraStar is one of them. So these are satellites that are literally the size of like a giant yellow school bus. Probably something like you could, did you guys take a bus over here, or T?
T.
T. Okay, well, a giant yellow school bus. Imagine like it kind of tipped on its side, and that you can climb up the stairs, and instead of seats in the bus, what you see are these walls of just electronics, just amplifiers. You can't send very high energy signals through wires because they'll melt the wires. So you have like pipes that you send them through instead. They're called waveguide. And so just imagine like this giant cell. You can literally climb into it with your hat on, like your bunny suit on, and your clean suit on, and your wrist strap so that you don't accidentally static discharge and break something. You just walk up the stairs and you like solder things on, and it's huge. And the solar panels are like the size of that when they deploy. So there's very, very big satellites.
These are the solar panels coming
Yeah.
off the side, and these are antenna. We're talking to the ground.
Yeah, so those things, and some of them are shaped like the continent of the United States because the beam's supposed to just hit the land. They don't want to waste the energy on the water, so sometimes those guys have like funny shapes in them. It's really cool. Yeah.
So we learned how to sort of commercialize space, right? You can make a lot of money with satellite communications or satellite television, so you can afford to build these really big spacecraft. You can also use GPS. Your phone has a GPS receiver, and that works by having a constellation of satellites that are all sending out where they are and what time they think it is. And then your phone receives, well, there's that satellite there and that satellite there, and you can triangulate its position. So you have to have that constellation, and they have to be very precise. So there's a huge constellation that's always getting refreshed of GPS satellites. For weather, you've seen satellite images of the Earth, so you can look at all different wavelengths. So you can tell, is there a dust cloud or is it a rain cloud? All different ways. And these are, again, enormous satellites. These are people in bunny suits and this big satellite. And then for astronomy, the field I work the most in, we have the Hubble Space Telescope, which was launched in the early 90s, but still going strong. We're planning to use it this fall. And then James Webb Space Telescope, which is planned to be launched in about 2 years, which is even larger and has this, it's going to be very cold. It's going to look at infrared light, much longer waves than your eye can see, and it has to be very cool, because otherwise it would just detect itself, because it has a temperature, and that infrared light, it would be sensitive to that, so it's blocking out the sunlight with those layers of.
Do you know how big those layers are?
How thick?
How many people here play tennis? Those things are the size of a tennis court.
Whoa. But they're like the thickness of foil.
They're like, yeah.
Wait, just the blanket?
Yeah.
It's on a structure that's literally the size of a tennis court, and it's, you guys know how like your coffee stays warm in these like insulated cups because it has the gaps in between? It's the same concept here. There's no air in space, but the gaps create insulated layers.
There was another question?
Astronomers want to replace the Hubble
Yeah.
telescope?
And
is there like any projects that anyone's working on to replace it?
Yeah, so for some science, James Webb will replace Hubble. So Hubble is good at seeing the light that your eye can see, visible light and even ultraviolet light. So the next generation of telescopes that we hope to launch like in the 2020s will be more like the size of Hubble and do similar science like in the wavelengths that your eyes can see, but be much more stable. And we don't have a space shuttle, so we can't go repair Hubble, so we're going to find to replace it and also put it out of orbit. Instead of Hubble goes around every 90 days, it would be nice if it was out past the moon and in a very stable orbit, so we didn't have to have it going into the Earth's shadow all the time, because then you only get to look at something for half the time. So if you put it out in a distant orbit, then it can just sit there and stare for hundreds of hours. Does anyone else have a question? So this is all part of a big system. Like to launch one of these spacecrafts takes a lot of infrastructure. You need big radio dishes to communicate with it. You need big launch facilities to launch it. And then you need the satellite itself. So it's sort of a systems problem. And you can see from back in 1957, when Sputnik was launched, the number of successful rocket launches, which is the green line, sort of peaked in the 60s and has been sort of bouncing around. This is 2014, so it's trending upwards there. You can see it's not, like, a lot of them fail. So this peak year, there were 140 launches, and almost 20 of them failed. So people like to say space is hard, because a lot of them fail. But there's been a sort of a somewhat linear decline in the number of failures. We're getting a little bit better on this scale of reliably launching spacecraft. But this is the launch vehicles per year. But if you look at the number of spacecraft that were launched up to 2014, that curve is going up much faster. So does anybody want to guess why that is? Why are we launching a lot more spacecraft but not launching more rockets?
Because we're becoming like, we get more access to more knowledge and stuff, and we want to know more about space. So, because new questions come up every time a satellite goes up, so if they send more satellites to figure out the questions.
Do you have a guess?
Well, it says that technology and imaging are two of the biggest fields of CubeSats that are getting launched. So I'd assume that technology and imaging, those CubeSats are getting launched from private companies for private endeavors like GPS, tracking, cellular stuff.
The reason that there's not as many rocket launches but more experiments is because the experiments they're making them in CubeSat, so they're smaller, when before they were big satellites, so you can fit more into one rocket.
So everybody's right. We want to launch more satellites because we always have new questions. We want, imaging satellites are a lot of those satellites. CubeSats are bringing down the cost and making it easier to do both of those things. And part of that's because we're sort of going back to simple spacecraft like Explorer and Sputnik that just have one off-the-shelf compact thing. And CubeSats are kind of the innovation there. Here's one of those enormous satellites like we were showing before. And this is where the CubeSat goes on the rocket. So you can put a CubeSat all the way around the base here, launch one rocket, one big telecommunication satellite. I don't actually know which payload this is. Oh, you were right.
That's the airplane.
Oh,
There we go.
you got it.
So did you guys know that, you guys have heard of like health insurance, right? When you get sick, everybody pays a little and then if you really need it, you can get paid up. So when Ewan was showing the rocket diagram, there's also insurance for rockets and spacecraft. So if your rocket blows up, you're not out $500 million because the thing you just built just exploded. So can you guys imagine what it must be like to get like an insurance policy on a rocket?
Who gives them the insurance?
Some very smart people who know what that plot looks like and can make money off of it and know just how much to charge to cover the ones that blow up.
And so if you own this spacecraft and you're buying insurance on it, and then you have a bunch of high school students or MIT graduate students who say, we're going to build a spacecraft, do you think they want to bolt it to the bottom? No, they don't let you do that. They take a box. It's hard to see in this picture, but a canister. I've got another one on the next slide.
It's like a
So
jack in the box.
This is the box that the CubeSat goes in. And then if we do something that causes our CubeSat to fall apart when we launch it, it's all protected in the box. And they're $1 billion telecommunications satellite, this thing. And I've got a video, I think. Yep. So there's a bunch of different companies that make these little boxes now, that CubeSats are a thing. So you put your CubeSat, so I get the cursor, I'll make it full screen. You put your CubeSat in the box, and you tighten the screws.
It's called torquing the screws. So there's special torque wrenches that measure just exactly how perfectly to tighten it. We're very picky in space. And then sometimes your screws break off anyway, and you just tape them off that anyway.
So then, once you get to space, the door opens when you're far away. Once you're in space and far away from the expensive satellite, the door opens and there's a spring that pops you out. So that's the CubeSat. We call that the canister, and then the CubeSat slides into the canister.
So about 5 years ago, we had this in our lab, and we were testing some of these, the smaller ones for the first time, and we had a spring set up and a table on the other side of the room. We had grad students on the floor with blankets to try to catch some things that were flying out, because we were trying to measure the velocity that it was coming out, just like a physics experiment. We wanted to know how fast it was coming out and how fast it would tumble. So.
What type of sensors are in the box for it to know when it's far enough from the expensive satellite thing?
So that's controlled by the launch vehicle.
The timer.
Yeah. And there's a timer, but there's also like a release, right? There's not.
It's a timed release.
It's just a time release. There's not a pressure. Okay. But the CubeSat usually has a switch that doesn't go until it's out of the box. So the CubeSat is off, and then it switches on because the switch pops out once it's not held in by the box. Question?
How does companies like see the orbit? Because like if you need your CubeSat to go in a certain orbit to like take pictures of like Mars or something, how do companies like get it in the specific orbit that they want?
So you know in advance the trajectory you're launching the rocket on. That's what all those women were doing at JPL. They were calculating the trajectory. Now we can use a computer to calculate the trajectory. But given the input and the number of berms on the rocket, you know what orbit the rocket's going to go into. And then you'll deploy your CubeSat at some point along, because the rocket has multiple stages. So at some point along there, you'll deploy the CubeSat to be in approximately the orbit you want. It won't be exact. It'll be close. And then someone will track it on the ground with radar and give you, oh, it's about here. And then you try and communicate with it from the ground. Carry us all.
The rockets have different stages. So you have the first stage to get you up, right? And then you have another stage that kind of gets you in the orbit that you wanted to go in. Then you release your spacecraft. The spacecraft might not be happy where the rocket put it, because it takes a lot of energy to go cross plane in an orbit, to go sideways, or to go up, or to go down. So you need more fuel. So either you have thrusters on board your satellite, so your satellite can get itself somewhere, or you have another stage, a third stage on the rocket that can deliver you somewhere else. But you need more you need more power and thrust to go anywhere. And so these little satellites, it would take them a lot, either a long time or a lot of thrust. A lot of, like, the whole satellite would be like this giant rocket to try to get them in a different place. So that's why deciding what rockets you go up in is so important, because that'll tell you whether you're around the equator, whether you're going over the poles.
Is there another question? So this is another way to launch a CubeSat. It's more unusual. But this is a little cube-shaped CubeSat that was launched by hand from the space station. So Cosma, Oleg, Artemiev threw it away from the space station. So instead of a spring popping in. So there's other ways to the point.
You must have really liked baseball.
So CubeSats have lots of, like, they get you above the atmosphere. You can just sit there and stare at the target. There's lots of rockets going up, so you can pick your orbit by, I want to ride on this rocket. I'll buy a little bit of space to put my deployer on. But they're really small, and they're hard to point. It's hard to know where they are. It's hard to have a big enough antenna. You saw the communication satellites had bus-sized antennas. So it's hard to have a big enough antenna to get much information down. And you are constrained by where someone wants to launch a rocket. You can't say, I want exactly this orbit, because you can't buy the full $100 million rocket. But someone mentioned imaging before. A big chunk of all of those spacecraft launches in 2014 were these Dove CubeSats. So these are CubeSats the same size as this, and this company, Planet, mass produces them. They make hundreds of them, and they launch them in batches. So they launched 100, something like 80 or 90, I think, on that launch, all at once. And then they're orbiting the Earth, and they're slowly drifting apart. So they cover slightly different parts of the Earth at different times. And if you want a picture of something, you can buy a picture of your bit of ground as their CubeSat is flying over it. They're just basically just like that rocket that they launched in 1947. It's just a camera and some solar panels and a radio, and taking pictures of the Earth. So you probably keep seeing this like 3U, 1U, all the CubeSats are labeled. So the standard for a CubeSat is a 100mm cube. So like almost about 4-inch cube. And then we add a number before that to say how many of those cubes it makes up. So how many U's do you think this is? 3U. So this is like this one here, micromass, and it's being chased by a 1U. And then the deployer you saw before was for a 6U CubeSat, which is about the biggest that is standardized now, but people are talking about building 12Us. I'm not sure if any have been launched yet, but there are people who are working on 12Us. They're just, but the freedom of working within the U system is you can say, I built the 3U CubeSat, this is exactly how big it is, I'm going to go buy a deployer, and nobody, well, they care a little bit what's inside it. You want to make it out of things that burn up so it can re-enter the atmosphere, but nobody's too particular about what you put in there. It's mainly that you fit in the size. You don't carry anything terribly dangerous, and then you can buy a canister, stick it on a rocket, and launch it. We can pass these around. So that one is a 3U model that has a 3D printed sides, and these would really be aluminum. Like this one here has actual aluminum structure inside. This one, these solar panels they don't have the silicon on them, but they're the actual type of solar panel and hinge that you would put on a real CubeSat. And this is also a structure from a company that sells kits to make CubeSats. So it's a Pumpkin. Is the brand that makes these kits out of aluminum structures, and then there's a Scottish company that makes the solar panels, and those are mock-ups of the Scottish solar panels. And then this is a mock-up. It's made out of aluminum, but it's not meant to fly. It's just the solar panels are just plastic. But you can unfold the big solar panel there and see how it will get you more surface area to collect more light, to get more power in space.
I have a question. For example, if you're just like a normal guy and you want to send a CubeSat into space, how much would that particularly cost?
It depends. What's the lowest? There are people who are selling 1U launches for a few tens of thousands of dollars.
A 1U launch right now is about $60,000. Which, you know, you could get yourself a nice Tesla.
Launch
Or
into
you could launch
space.
your CubeSat
That costs a little bit more.
But if a school builds one, NASA or other organizations will often, or the United Nations will often launch ones that were built for education.
So basically, somebody has to go through the pains of writing a stack of paper that describes exactly what you built and why it's cool. You send that to NASA, and then they say, okay, great, you're in line for a free launch. Your rank is priority number 6, and your launch cost can be up to $300,000. And we'll cover that for you because you're teaching young people about how to do space stuff. And we need more young people to learn this so that they can come work at NASA and keep building rockets so that we can build this lunar gateway that we're planning. So they have reasons.
And that was something that was on my slide, but I didn't mention it. I got paid to go to grad school and build those rockets. So don't worry about grad school being expensive, because NASA really wants people to go to grad school to learn how to build spacecraft. So if you go through undergrad and you graduate and you look for programs that, and even in undergrad you can find scholarships to learn, do aerospace engineering or physics and learn how to build these things, because there's a lot of desire to train people to do this. So, you know, they pay me to launch things in space. It's sort of a hard deal to turn down. These are examples of CubeSat science. So the one on the left is the Radio Aurora Explorer. That's measuring radio emission from the Aurora Borealis, the northern lights. The one on the middle is called Oreos, and it measured gravity and radiation and effects on microorganisms. So
Unfortunately, there were no cookies involved. It's very disappointing.
but there were living things, right?
Right. Well, people send things into space all the time. Most of the stories have a very sad ending, just preparing you.
Yeah, if you want to launch something alive in space, don't expect it to happen. And then the lunar cube on the far right is an ice.
Sorry.
If you like humans, they don't come back.
No, humans don't have. It costs a lot more money than launch. Than $60,000.
We should be very respectful though, because several people have passed away on the ground during testing as we went through the manned spaceflight program. And even now, as people are doing more with Virgin Galactic, and there have been test pilots that have not made it. So I mean,
And when I was
it's
before I went to
serious
college,
engineering is just a problem.
when Columbia reacted. So people have died on the way back in. But in terms of CubeSats,
It's not very frequent, but still.
In terms of CubeSats, there's lots of different science projects you can do. And some of the ones other ones that we've been doing at MIT, this is very much like those Dove CubeSats I showed you before, but a much more precise camera that can measure the brightness of things very accurately. So if you had a candle flickering thousands of miles away, you could tell you how bright it was in parts in a million. And this is called Asteria, and the idea is to look for planets going in front of a star. So if your planet goes in front of the star, it blocks out a little bit of the light. So if you measure all the light from the projector, and then when the planet's not there, it's a certain brightness, and when the planet comes in front, it gets a little dimmer. So that's what this CubeSat would do, and this was launched from the space station. And this is Professor Seeger in the Earth and Planetary Science Department here at MIT that worked on this. And then we already talked about Murata, the microwave missions that our lab has built. And we're building this one, Denny, to test deformable mirrors in space, which are mirrors that can change their shape
while they're in flight. And that's going to be a 6U, like the big mock-up there. So we mentioned before that it's all sort of a system. So one of the things is, how do you keep track of all these different parts and make them work together? And there's actually a discipline called systems engineering, which is basically how do you do that? How do you know that when I put this camera inside this spacecraft, it gets the right power, it will survive for the length of time it needs, it has the right resolution, and it's going to point in the right direction. There's all different engineering challenges to make that happen, and systems engineering is the discipline sort of keeping track of that. And you usually do that with sort of mission objectives. What do you want to do? So that first camera that they put on the rocket, they just wanted to take a picture. And they wanted to get it back so they could see the film, right? Because they didn't have a radio. So you have to, you set big mission objectives. I want to take a picture, and I want to, get the film back to the ground.
Did you know they used to send them back in parachutes and then chase them down with helicopters? The film canisters on the spy satellites? No joke. Sorry, I'll shut up again.
Wait, was that Helix? What's the? If they want to look at the Wikipedia page.
Paragon.
Paragon, but there's one that started with Hexagon.
Hexagon.
Hexagon, wasn't it? Or Paragon? Okay. These were basically before Hubble. The same satellites existed, but for spying on the ground. But they used film. Hubble uses radios and digital cameras. But before that, they had to get the film down. So they drop it over the Pacific and then try and catch it with a plane as it came down.
Before it went in the water and they lost
So
Or somebody else got their hands on.
Then, so you decide, so the key word that systems engineers love is requirements. This is what I learned when coming to MIT, because I was a scientist before, and now I hang out with engineers, and they love requirements.
We hate requirements.
What is required of the thing, so we can build a thing that works well enough that it meets its requirements. So you can have very complex requirements that say, I will, have exactly this many pixels in my detector, or my, the car is going to have exactly this number of bolts in the rim. Like, you can design anything to have requirements. Then you have to know how they interact. Like, okay, someone built the wheel, so I have to set our set of requirements so that when someone puts the wheel on the car, the wheel matches up and the bolts are the right size. And then that all flows to the big requirement of having a car that drives. Or if we go back to the camera analogy, like, you have to have the camera fit in the top of the rocket. So you have a requirement on the size of the space the camera goes in. And then you have a system description, like lots of documentation to define your system. And then you try and make it better. Like, can we get more performance out of this system? And then we have to do tests and validate that this thing we built with a set of requirements actually does what we wanted it to do. Does it actually take a picture? Does the car actually drive somewhere? So it's just sort of a formalism. It's a lingo that is very important to something as complicated as a spacecraft. And I don't actually know, this is Carrie's slide. I don't know what INCOS.
It's a systems engineering body. They're regulators for everything. So if you.
So this is the definition of a system?
Yeah.
Okay.
A bunch of things that you put together. So one of the nice examples of a system that I like is putting things together so that they have a new function. So if I handed you a jar of sand and a funny shaped glass, the fact that you can combine the sand with the glass and get an hourglass and tell time is combining elements to form a system that has a new function. Does that make sense? Okay. That's what systems engineering is. It's putting things together so that they have a new function.
And then we've got lots more detailed slides on that. But I'm going to skip ahead. So for a
Nick's like,
spacecraft,
that was it.
for a spacecraft, you have a set of systems. You might have your payload, so that might be your camera. Then the bus is like your school bus, the thing you ride on to get to space. So the school bus is the thing you ride on to get to school, the bus is the thing you ride on to get to space. And then the bus is made up of all these parts. So your bus has a structure. It has, a metal frame, holds the wheels on, mechanisms like the engine and the parts that hold the spacecraft together and cause it to move, power, so the engine and the fuel, or in the spacecraft, the solar panels, attitude and orbit control. Now your bus probably doesn't have orbit control, but this would be sort of the steering system. So attitude is how are you oriented in space? So if you turn the bus, you've changed its attitude. So this is turning the spacecraft. Telemetry and commands. So this is how you communicate with it and what you tell it to do. Thermal is does it stay the right temperature? Is the air conditioning working on your bus? Data handling is how do you communicate between the parts of the bus, and propulsion sort of ties back into the mechanisms and the power, but it's how do you get where you're going. And this is not, I didn't make this slide up for you guys. Bus is the technical term. This is the systems engineering slide from Carrie's graduate class.
Yeah.
A bus is I'm just making the analogy a
But
little
bus
extra.
is a thing you put things on or into. So a spacecraft bus is the thing that you put the instruments on. In electronics, in my computer, the data bus is the wire that all the data goes back and forth on.
It's like how an Airbus isn't actually just a flying bus.
Right. So in a way it is, but yeah.
So I'm gonna quickly go through a few of the challenges in space and getting to space, and then we'll probably have a breakout in a bit. But let me first tell you about some of the things that make it hard to get to space. So this is a lot of words. Basically, it has to survive the launch, and people like to reuse. So heritage is a word that space gets thrown around a lot because if it's been in space before and it worked, it'll probably work again. So that's sort of a key word to remember is heritage. Has this been done before in space? And so you want to know how long your CubeSat's going to last. So you could have a CubeSat that lasts 9 days, or you could be building a mission, or this is the development life cycle. So this is how long it takes you to design it before you get into space. So Planet Labs can turn around a CubeSat in 9 days. NASA can turn around a spacecraft in, well, they're going on 24 years for JWST there on the bottom. So let's see, let's go to some more fun stuff. Launch dynamic environment. So this is when you're launching what happens to your spacecraft when it's on the rocket. So you lift off, and then this plot shows you acceleration. So this is in G's. So we're under gravity, so we're at 1 G. So your rocket starts off at 1 G, and then it starts to move, so it has to be accelerating away from Earth. And then you hit a peak of for this particular rocket, like 5 Gs. So if you imagine gravity being 5 times stronger, that's going to deform whatever you're launching. So you got to worry about that. This is how hard the engines are working, and then this is dynamic pressure. So this is how hard the air is running into your spacecraft. So at some point you're not moving very fast, so you're not pushing against the air very hard. And you start to speed up, and then you hit a point where the air resistance is strong. Once you get high enough, though, there's no air. So then it starts to fall off, even though you're going faster and faster. So that's what, if you watch a rocket launch, like a SpaceX launch, they like to talk about max Q. So max Q is that moment where the air pressure, so like the wind drag in your face when you're riding hard on a bicycle, when that feeling of the air pushing against your face is maximized, is max Q for the rocket. When before it starts to run out of air, but it's still going faster and faster. And then here, like we were talking about before, there's multiple stages. So it started out with 2 little stages that pop off, and then you open the fairing. So now your spacecraft is exposed because you're above the atmosphere. And then you have a little second stage that drives you, and then fewer and fewer until you get to the last stage, and your spacecraft is in orbit.
So it takes about like 3 minutes to get into space from Earth.
Sorry. It depends on, so if this, you can get into space faster, but then you have to accelerate harder. So then you're putting more stress on the thing you're putting in space. So the space shuttle was very gentle, right? Because there's people in it, and you don't want to, turn them into jelly. So you very gently go into space, and it takes a long time. The very fastest rocket would go very quickly, but you'd have to build everything really sturdy to survive that, so it gets more expensive to go faster. And this is just another graph that shows the same sort of thing, except in terms of vibration. So how much is the rocket shaking? And I think I have a better slide. But it shakes a lot at the very beginning, and then at max Q it shakes a lot because the pressure was really high, and then it sort of dies out, and then there's a shock wave when the engines turn off in this particular example for an unknown vehicle. And this is where there was all that vibration at the beginning. You can see the shock wave from this rocket ignition. You can see the shock wave coming out of the exhaust tubes. And you can see this plot is sort of color-coded to show you the pressure of the air. And there's a lot of pressure in these exhaust tubes and a lot of pressure around the spacecraft. So these are all things that are going to shake, rattle, and roll your spacecraft, and you have to build it tougher in order to survive that.
When people start in order to determine what type of metals or substances would actually survive for the launch and also surviving in space, did you guys do a bunch of trial error, or were there sensors or monitors or readings that you took from one rocket to determine?
So there was a mix. I think they got a sense of what space was like with the early experiments, where they measured the density and the number of micrometeorites, and then they said, well, this class of materials will probably hold up. And then it gets a lot harder when you worry about radiation in space and whether it damages your electronics. But in terms of just what material will survive being in vacuum, we also have vacuums on the ground, so we can put it in a vacuum chamber, pump all the air out, and see if the thing survives. And there's something you might run into when you're building your CubeSat is called outgassing. And I might have a slide later, but the idea is that your material starts to bubble. So if you put your potato chip in a vacuum chamber, right, and took all the air out, it'll start to boil, and the material will come off. And it'll coat the inside of your vacuum chamber. If you put your potato chip in space, the oil will bubble off and coat all of your electronics in your telescope optics. So what you want to do is send something inert, like a block of aluminum, that won't boil, that's a solid. So it gets tricky with plastics, because some plastics, when they're in a vacuum, release a lot of gas. Like you can smell some new plastic smells, right? Some doesn't. And usually that plastic that has more of a smell to it will boil off more material in space and be more of a risk for contaminating things. And that's one of the things you really want to worry about, especially when you're a guest on someone else's spacecraft. That box isn't a tight enough seal to guarantee that some of the chemicals won't boil off. So that's one of the exceptions. They do care if you put a bag of potato chips in, and then you open the bag, or if you assume the bag will burst when it goes into space, they wouldn't like that even if it was in the canister, because then you'd be getting all this volatile material all over their spacecraft. So they only want inert things that have a low outgassing is the keyword there.
On the second bullet point, it says the spacecraft that's acoustic. What does that mean?
Yeah, so you can have sound waves inside here and traveling down the structure. So that's just the vibrations in your the range of your ears, and traveling, especially, they'll get translated to the spacecraft by air in the fairing and just along the edge outside. So it's vibrations, but acoustic vibrations.
To control the vibrations in the rocket, is it a mixture of shaping it and the material, or just the material?
Both, yeah. It's an optimization problem for both those things. And this is sort of how you've got wind coming in at an angle, you've got the vehicle going up, you've got the motor going off, and all of those things are building up. So you could have your rocket could oscillate really slowly along its axis, or it could be fluttering up here from gusts of wind hitting the nose cone. And all those things build up to give you the sort of what we call a spectrum, a range of vibrations at a range of energies that are shaking your spacecraft. And I think I've got a video. So the way we test this is we try and see if it'll break on the ground first. So we use these things called shake tables that vibrate and try and see if the thing will fall apart at a realistic input.
CubeSats, are they meant to go up to space and stay in space and deteriorate in space when they come back down to atmosphere or come back and they'll be able to collect it?
They are meant to not survive re-entry. So that to be a CubeSat, you have to last not more than 25 years. So you have to be able to show that your CubeSat will come back into the atmosphere within 25 years, and that it'll burn up completely on the way down. So if you wouldn't build it out of a solid block of titanium, because that might make it on the way, make it down. But an aluminum structure like this, that's mostly hollow and thin in aluminum, that'll burn up on the way down. And that's not usually a very hard requirement to meet when you're building something this small. So I have a great video, not from space, but of how we test things. So this is the exact same idea for how we test spacecraft. UPS does it for packaging. They build up the spacecraft or the structure, and then they put it on a shake table and vibrate the structure. And so there's a pneumatic deck. Sometimes they use speakers, and you try and break the thing. They're using the input from a truck rather than the input from a spacecraft. But this is actually really important because oftentimes the worst thing that your spacecraft will experience is the truck ride to the rocket. Because truck rides are actually worse usually than rocket launches. So this damage to this UPS box is realistic. This is what you actually want to do to your spacecraft. You don't want to test it like it's going to go on a rocket. You want to test it like it's going to ride into a yes or no.
Well, the rocket too. I mean, we're slightly exaggerating, but yeah.
And that's exactly the idea of bouncing. Usually, the rocket might be a slightly higher frequency, so bouncing a little quicker and not quite as far, but the same idea.
And then when the rocket stages separate, there's a shock, which some people test by literally putting their spacecraft on something and then hitting it with some type of hammer, or I've seen people put the spacecraft on very hard granite tables and use a nail gun and fire it next to it to shock it.
So this isn't actually...
So these ice rock tests that you have to do, like they have an analog.
This is an actual CubeSat getting vibration tested, and you can see that it's the same thing. They're on a table and they're bouncing. And luckily the CubeSat doesn't start to bulge apart like the cardboard box.
So more about the shape of the CubeSat makes it so that it can manage those vibrations.
So you engineer the structure to survive the vibrations. Being a cube doesn't necessarily make it better or worse. It's you just have to make this stiff enough, and you have to, like Carrie was mentioning torque before, you have to make sure there's enough force holding the parts together. So if you take two pieces of metal and screw them together and then leave them on your desk, they're not going to go anywhere. But if you're going to subject them to all these vibrations, they might come apart, right? So you need enough torque that the mass of the one bouncing away from the other will keep them tight together. So you have to sort of go through every surface and every structure to make sure it's going to be tight enough and that you have a thick enough wall of aluminum that it won't deform when it's shaking.
Why do we not want it to last more than 25 years?
Because you don't want to contribute to space junk. Space junk, yeah. So there's a lot of stuff in space and it's accumulating. And eventually, the risk grows and grows that one spacecraft will run into another spacecraft. And when they collide, then you have lots and lots of pieces of space junk, right? Because they blew apart. And then that increases the risk of another spacecraft getting hit, because instead of having 2 things flying around, you had hundreds or dozens of things flying around in all different directions. So then they might hit something else, and you can have a cascade effect of more and more space junk. So you want to limit the amount of stuff you put up, and you want to be sure that it will come down in a reasonable amount of time.
Does anybody know how they keep you from putting stuff up into space right now? Who's in charge of, who sets these rules? Nope. Next.
Military?
Nope.
President.
Nope.
People in charge of the ocean.
The people who are in charge of your radio and television broadcasts.
The FCC?
The FCC. How does this work?
What?
What?
It carries fomenting revolution.
They can't use for putting stuff into space.
Because
They put up a lot of satellites.
Up there. They have their satellites that, protect communications, and they don't want more space junk to
They're kind of like a puppet. If you have a satellite, you have to talk to the ground somehow. And right now, the only way to do that is with a radio. And so they're in charge of who gets a license to transmit on a radio, like amateur radio licenses. Just like if you're in Boston, you want to call a cab, before there was Uber and Lyft, they had to have a license. So the FCC issues these licenses and says, yeah, you can transmit your radio at this frequency for this long over these places. So they're in charge of saying who can and can't do that on spacecraft. So before you go in the rocket, you have to submit a form to the FCC and get approval to turn on your radio from space to ground and ground to space. Otherwise, they don't let you go on the rocket. And if for some reason you've gotten on the rocket and you've been integrated, and you're just like, oh, just wait, my paperwork will come through. It'll come through. Just put me on, and then it'll come through. If they find out at the time of launch that you still don't have your license, they will zip lock your deployer closed so that you can't be deployed. This happened all the time except for once last month in March. Or actually, it was in January. It was it hit the news in March, where somebody snuck 2 little satellites onto a rocket without licenses for the first time ever, like
Is it
since
like the carpet
1960.
Like
Little ones. And then they had applied for a license, and the FCC said, no, we're worried about you guys being space junk and hitting the space station, and we won't give you a license. You're not safe enough. And so they said no, and they went up anyway. And now it's going to be very, very interesting to see what happens, because what are they going to do? Like chase it up there and take it back down?
And if you figure out a way to talk to your CubeSat without a radio, then does the FCC have any jurisdiction over it?
Well, so if you weren't using a radio, what would you use? Yeah.
Lasers.
Right. So who regulates lasers? Who regulates lasers in the United States right now?
The military.
Nope. Here we go, guys.
Guys, again.
Who's in charge of the lasers? Anyone? Right now, the strictest enforcement on laser usage in the United States is the Food and Drug Administration.
How does that even correlate?
Now give some to Jeff. How is that even correlated?
Because you don't have lasers.
I didn't even think Oh, I got you.
So I think we're going to take a break from making you sit. We want to give you an opportunity to draw on the wall. So the challenge, though, before you get to write on the wall, is you got to figure out what it would take to put your cell phone into space. And what would you learn with your cell phone in space? And so break up into a few groups and try and cover these questions. So like, what are the mechanical problems, the electrical problems, the software problems, the systems problems, and then you got to think about all those things on the systems engineering diagram. The structure, the power, the attitude control or the position and aiming, the steering system on your school bus, your communications, your environment, your propulsion, how does your phone propel? And then, so you got to come up with a list of the issues and the engineering solutions for the challenge of launching your cell phone into space. And then you've got to draw pictures or make a list of the challenges and solutions on the board. So maybe do groups of 4. So you've got someone in each of these categories.
Can I also make a suggestion to have the schools kind of
Yes, that would be great.
Yes.
So we can alternate across the table.
And you guys can come grab some cookies or a snack while you break up into groups and decide who you want to go by. And every group can get maybe a marker, so you can have a section of the board to write on. There's some markers all the way. Avery's going to have the markers if you want to grab them.
You actually sit back down for just 2 seconds. We're going to count you guys off. Almost. Yeah. Almost. We're going to count you guys off. Remember your number.
We're going over now. You and which team are we starting with?
We're starting with green.
The green team, are you guys ready?
Why?
So, do you guys have like a team speaker, or are we going to go through each one?
Team Green, do you have a nominated leader?
Oh, we decided on going through each
One.
one.
That's great. That's great. Go
And make sure you say your names and your school before you start talking, just so everyone knows.
Okay. So my name is Jefferson from O'Brien. So for the mechanical aspect of our satellite, in order to put the phone into space, we thought that we should think about insulating canister and also temperature regulation for circuits, because we know that we're going into space, the temperatures, it might make it so that the phone might not survive and not be operational in space. It might be too cold for it to actually operate. So we thought we should definitely think about that in terms of electrical management there.
How cold do you think it gets in space?
I don't know how cold. It must be pretty cold with the suits and regulators and ships.
Well, there's no air.
There's like one, it depends on which school bus that acts up its helmet and froze.
So yeah, so if you're on a spacecraft, like if you're putting your phone on a spacecraft, or if your phone is a spacecraft, the flatter and thinner you are, both colder and hotter you get. So when the sun's on you and you're flat and thin, you get really hot really fast because you don't have enough area to let the cold of space kind of bleed that heat away or radiate it away. And if you go into the eclipse side where you're not in the sun anymore, so the Earth's in shadow on one side, and if you're in low Earth orbit, you're going around, anybody want to guess how long it takes you to go around the Earth? 90 minutes. Okay, so you have 45 minutes when you're just freezing and 45 minutes when you're warm. So you can be as cold as, if you're on a solar panel, you can be as hot and cold as like minus 20 or 30 degrees C up to like 120, 130 degrees C. So you can get like, yeah,
we actually skipped that slide.
really, really hot and really cold. But if you have a box and you have things in the box that are using a battery to stay powered and they're all kind of touching each other and the radiation of heat is kind of within the box, you can stay like where electronics like to live, which is like minus 10 to like 50 or 60 degrees Celsius.
My name is Andy. I too also go to O'Brien. So for software, we thought of some stuff like a picture timing system in which, like, after a certain period of time, it would just randomly take a picture of like space itself, either be behind the Earth or like towards the sun, like the stars. We also thought of like a streaming system where basically like it just select the activities in space for like an audience online to see. And for storage, we just thought about like we have to work with the storage because there'd be like a lot of pictures taken, and it would be like a very high capacity to actually store all those images and videos.
So for systems and engineers, we thought about how we could remotely control the phone, so we could do voice control and open up the microphone or the streaming system, depending on what we want to do. Plus photo taking as well, and managing storage, because we probably need to use a different phone than like an X or a 4, because as you mentioned earlier, the thinner the phone, the more change is going to have in temperature. So you don't want a super thick phone because that's
You could design around it.
that's true. But like the more basic phones, they don't have the complex systems that we probably want to use. But then the more advanced phones don't exactly perform the way we want them to. And then also pressure and gravity regulation. With the internal components of the phone, we also want to regulate those so it doesn't mess up anything that we're trying to measure.
I kind of love the idea of voice recognition on a satellite. So you would have to have essentially some type of way to radio your voice up there. But you could, if you had that kind of like machine learning on a satellite where you could just have it recognize the voice and then the commands, that would be really interesting. So I kind of love that idea.
Alright, my name is Felix, I'm from O'Brien, and as for battery capacity, because we know that energy and having power on the satellite is really important, we thought of using portable battery, and instead of using a standard portable battery, we want to use solar panels. And we also thought about, for propulsion and aiming and positioning, we thought about just sending out like a CubeSat, and by putting it on a regular rocket and just having maybe an astronaut or like just like a CubeSat to be sent out by Jack in the Box style, basically.
CubeSat potato gun.
Cool. Anything else in this group? That's all for you?
Good work, guys.
Very nice.
Let's do this team black and blue.
Brown, blue,
Brown, blue, red. Okay.
Yeah, we'll start with blue.
Finally found a good marker.
Alright, my name's Ewan, I go to the O'Brien, and the way we found out to solve our electrical problems was, for example, radio was a problem, so we included the antenna. Temperature was a problem, so we kind of decided to like, darker colors attract like more heat, and lighter colors attract like less heat.
That's right.
So we decided to like change up the color. For our radiation, we found out that we have to do some kind of radiation protection.
So how do you protect things like when you go to the airport? What do you and don't you put through the X-ray machines? That's radiation. Yeah.
There's like certain kinds of materials that will protect. So for example, in like film bags for like X-ray film bags, lead is a good example, even though it is poisonous. It still protects from radiation, and it's known as probably the best material that will protect from radiation.
Anything that's really heavy will keep energetic particles from getting through it. It will make your phone heavier.
For sensors, we will seal off our sensors, keep them safe. When it comes to battery, lithium ion explodes in space, so we chose to go with nickel-cadmium batteries, and we decided to recharge our batteries by using solar panels, so our phone can keep going.
Yeah.
No.
And we'll also include an altitude sensor to see like if it's going too high, if it's staying too low.
And also to turn the phone on, like when to turn it on, use the altitude sensor to turn it on at a specific height.
That's good. Assuming it can get altitude information, a very good thing to do. Let's see. So one of the thoughts here that I had on the batteries was you can actually send lithium polymer batteries to space, and it's a degradation in the way that the chemistry of the inside of the batteries, that the catalysts that degrade over time and can get thermal runaway that causes them to catch on fire. So as long as you're designing it well, you can actually use them, but you do have to very carefully monitor your battery in space. So that's really good. And a lot of people do use nickel-cadmium batteries.
So I'm Julie, and I'm affiliated with the Dexter South Field. So the next part is mechanical, the problems that we had is launch, debris, and then also outgassing. So for launch and debris to protect, to make sure that it doesn't like break apart, we're going to use a sturdy aluminum triangular structure, as we have drawn here, and also I did like a full drawing thing here. We will also have a sensor for micrometeoroids so that we know when one's coming, so that we can so we know
Like a LiDAR.
yeah. And then also for launching debris, there's also for the materials that we use, we will do a stress test for like compression and tension, mainly compression. And then we also have the outgas as a problem, so for that we're going to check the materials to see how much they outgas, and if they do outgas, to change the material so that that doesn't happen. And then also radiation, to protect from radiation. We will check the materials for like radiation exposure, what they do, because if they don't do it, like if they actually harm the phone because of the radiation exposure and they cause secondary radiation, that could harm it, and so we would need to check for that, and if that happens, we would also need to change the material.
So I'm Pastor and I go to Brian as well. I'm in the software part. So for this, we want to be able to basically communicate with the phone, so we need some sort of communication code with it. And if there's like any unexpected errors that happen, we also need to have backup programs within it as well, just for safety measures. Most likely use C++ to do it.
So you guys heard of single event upsets, or what happens when radiation can come in and affect bits, right, in computer programming? So it's great to be able to have active control and be able to reset a program. So it's good.
Why did you choose
Never want to
C++?
send anything to space without being able to turn it on and off automatically if it's not working right. So you'd, in your software, for anything that goes in space, remember this later. Always have what's called a watchdog. That's like kind of looking at events and counting up faults, or even just a timer that if you don't hear from the ground commander, or it doesn't reach a certain state, that it completely powers itself down and then comes all the way back up. That's super important in space.
Life lessons to live by.
Why did you choose C++?
It seems like well, it's actually one of like the better programs.
Yeah.
Cool. Anything else?
Yeah, for systems, like basically we said that we're gonna use C++, and it's like the same thing as the software. Like we have to make sure like everything's working properly, and like we can communicate with the code, and in case something happens, if someone wants to try to hack it, we're gonna have a backup.
No one's gonna try to hack it if we're talking about this.
Actually, people do try to hack satellites, and you have to use encryption to make sure that they're safe. They will absolutely try to commit your satellite to do things that you don't want them to be doing.
And that's also why we have backup codes.
We're gonna hack a cell phone.
It's a Nokia, by the way.
They don't know what you're doing out there.
I'm pretty sure they would want to hack like a military satellite.
They don't know that you're not a military satellite. What if the
Maybe they're looking for
military
practice.
Yeah.
Sure. But we're probably gonna like.
Maybe you're like the whole program is a decoy for a military chip that's in the middle of that thing.
So we're also like we're going to use like a simple phone, and so then we're gonna wipe the entire thing and like do our own like entire like operating system and code, and just code everything from scratch like from the beginning.
She's gonna do
Ewan.
So, orange. We sort of came up with a list of issues that could arise through just general wear and tear from rocket and also just from being in space. That the plastic could melt, rather that the plastic around the phone, if we're just using like a normal iPhone, they're plastic components, and those could melt through overheating because of the program, and also just from being in the sun, overheating from the launch radiation. Screen could crack during the launch. That being the camera would be pretty bad.
Also other components could crack, not work correctly, like the GPS. If we can't find where it is, it's really hard to get a signal down and up from it. Electrical discharge happens sometimes. Cheaper phones happens more often. We were thinking of going just with a normal iPhone. You know, I know how that works. Easy to interface with. You know. Will the phone be able to handle the pressure and lack of pressure? Will it break under the vibrations of the rocket? Okay.
So venting is a good point. What happens if you go from pressure to vacuum and you have like air inside?
You have to
Will it
let
expand?
You have to let it go out so it doesn't.
I mean, drilling holes is a big thing for space systems.
Go ahead.
So, to solve some of these issues.
What's your name? Which school you're from?
Oh, my name is Davey. I'm from O'Brien. And, yeah, so another issue could be the power. But some ways to solve these issues would need to be you could provide solar panels so that your phone could be powered, not just relying on its battery. You could for the launch, you could use different materials, or you could provide different structures like a pyramid to make it stronger and give it more stability. As for the electric discharge, you can, the course that the satellite takes could be in, I think, in the magnetic field, so when...
We're all in the magnetic field, so that's correct.
Yeah, but isn't there like gaps between it?
So the radiation belts have gaps. There's a lot of energetic protons that are about 1,000 kilometers up, and then energetic electrons that are about 10 to 20,000 kilometers out. So depending on how high up you go, you're either getting more radiation or less.
Yeah, and so you could like avoid those areas by...
That would be a great idea.
Yeah. Like different trajectories, and for the outgassing, you can just make it out of metal, so you don't have to worry about the plastic at all. Or you can use different silicones with different chemical formulas that don't allow for outgassing, and
Are we missing?
Alright, so next is going to be software or electrical? I
Take
have
one.
software. I have
What's your name? What's your
name? My name is Ashley, and I go to Johnny O'Brien. So, I don't know. Alright, I guess I'm going then. I'm Ananya. I'm from Dexter Southfield, and okay, electrical issues. So the phone has a short battery life, and I don't know which other group said this, but to solve that, yeah, we would use solar panels to power the battery. Electricity could burn the wires or the components, like with a lot of electricity just overpowering the motherboard or circuits. We can have issues with static discharge, excuse me. And electricity also means heat, and too much heat will destroy the components. And if the satellite is used to measure something, you know, heat related, I don't really know what you do with a phone and heat though. Just make sure that the satellite isn't measuring the heat it's producing itself. Yeah, that's it.
So there's an app that you can put on your phones. Your phones actually have a lot of little sensors on it. So if you went to the App Store and looked up like SensorLog or something like that, you could use your phone for lots of things. Temperature, pressure, You can see the gyros, which keep track of which way you're tilting it, so it knows how to reorient itself when you're using it. And you can see, yeah, you can just look all that up and you can put it on your phone. It's a lot of fun to play with.
There's a lot of different objects. It's very fun to explore.
And our last issue, I'll just introduce myself. My name is Ishmael Ashray. That's John D. O'Brien, and it's software issues. So one of the main problems with software is that the littlest mistake can ruin everything. And so, like, basically, perfecting your code before you even send it to space is very important, so that it's 100% going to run. Because once it's in space, I don't really think you can change your code.
That's a good question.
Or like,
that's a great question. What do you guys think? If you could,
you can. It would be hard.
You have to design it, right? You have to design it to do its own boot loading and have an image somewhere that you're either uplinking or getting from somewhere to boot load, right?
There's going to be a lot of data to send up depending on how big your operating
So
system is.
not all satellites are reprogrammable. Some of them are and some of them aren't. That's a really good point. So either you really want to test it perfectly or put in the extra time to make it to be able to be reprogrammed.
Second major problem is sending and receiving info. First, like, you need to know how you're going to be sending the information, either by radio or laser, and you have to have a license for that. And what are you sending? Because that can't be like sending something that's like too big. And if you like, when they did with Explorer 1, they just the Russian rockets, they just sent up a camera, but they had to retrieve the camera before it ended up like on the ground. You would need to like figure out how you're gonna do that, how you're gonna get your information, and how it's gonna be sent to you, and how would the software react with radiation or the mesosphere, or yeah, what she said.
Like in the mesosphere, there's ionized particles. You never know how that might mess with, electrical stuff and software too.
And for the limited Wi-Fi in space, just like as space.
There is limited Wi-Fi.
Limited. So yeah, so about the space station, we'll pick up an episode of Netflix.
Not the real question, what show?
Nice job, guys.
Thank you.
So our group was basically looking at it.
What's your name?
Oh, I'm Elijah. I go to the O'Brien. And basically for our mechanical, first we thought of the launch, because obviously without a launch it wouldn't be able to go into space. And that could obviously, like many groups said before, that could cause problems if it went wrong. And we also looked at like temperature, like other groups said, how like pressure and like the heat, or how hot or how cold of the phone can be, can like mess it up. Like if it's too cold, the phone might freeze. If it's too hot, overheating. And then we also looked at it from a money standpoint, because like it would cost a lot to do. And because for one, the phone, obviously, and like we used, as the group in Orange used, we just used the iPhone as a base. So basically, obviously iPhones are getting more and more expensive as time goes around. So that's gonna have to cost. That's gonna cost a lot than the making the satellite, making like the rocket to send up to space. And
Cost is a great point. So you'll have budgets for different things as you design a satellite, as I learned in Carrie's satellite engineering class. And cost is one thing that you have a budget for. Communication and bandwidth and how much information you can send is another thing you have a budget for. It's good to keep track of all of those limited quantities.
What do you guys think costs the most money on a satellite?
The fuel.
What's the most expensive thing about building a satellite? Not the launch part.
Launching the register.
The bandwidth.
Computing board.
The license.
So the most expensive thing about building a satellite, if you're doing it in the real world, like at a company or in NASA, is the people.
Oh, I didn't know we were putting that into it.
Yeah, so that's the most expensive thing is you have to, more than almost any hardware that you'll ever put on a satellite is the people hours that you have to pay for to work on it. So you need to pay all your engineers, you need to pay all your software guys. And so the most expensive thing about it is all the people.
Luckily, we are all minors.
We're getting it for free cheap labor. It's child labor, that's illegal. No.
They're on to us here. What have I done?
I know.
Good point.
That's recorded.
So for electrical, like many those two groups said, battery life is really important. So we're also thinking solar panels.
Do batteries like to be hot or cold?
Oh.
Medium.
Medium. Let's vote. Who thinks batteries like to be warm?
What about superconductors?
Batteries. Okay, who thinks batteries like to be cold?
Oh, my phone turned off in Minnesota when it was like -30 degrees.
Batteries like to be warm. Batteries like to be Solar cells like to be cold. Batteries like to be warm.
And then temperature is also important because it can be like what was the group said. If it's too hot, it can overheat the phone or stuff inside it. Yeah.
My name is Amlak. I'm also from O'Brien. Software. So for the software, the communication to cell phone towers and also unknown.
I'm Jonathan from O'Brien.
This time for everybody to be there.
Because I did this part mostly. So communication to cell phone towers and also the information that we don't know. I don't know a lot about cell phones. So there's that. And I'm pretty sure they just communicate with cell phone towers to get their information.
Or mini cells.
Alright, so they're pretty.
Do you guys know like this building probably has like a zillion little transmitters for cell phones in it?
Clearly O'Brien doesn't.
And they're pretty far away from most of those, so that's going to be hard to do. And also who's going to operate it, and mostly who's going to turn it on, because that's pretty hard to deal with. Also, this is pretty important here. It's not built for space, so it's probably not a great idea to send it into space.
So now, without assuming, I should have you guys, when you do get your devices back, you can all Google PhoneSat. And read more about this. And how it was the start to one of the biggest CubeSat companies that exists right now.
PhoneSats.
Any other thoughts?
Okay, we also need to consider like battery life, like make sure like you don't spend too much power, so control the battery.
That's a really good point. Battery, there's something called depth of discharge. You never want to drain your batteries all the way down to keep them happy. You want, for the charging and recharging, you want to drain them like 30%, and then recharge and 30% and recharge. This is not true for all batteries like your laptops or your cell phones, but for most of the space operations, that's what you want to do to get the most life out of them.
Cool.
Good work, everyone.